I'm Anil Kumar. Welcome to my series on hyperbolic functions. Let me first thank some of my subscribers who really insisted upon my creating these videos. Thanks to all of you for watching them. Now, since most of my subscribers are high school students, for them this could be a very high level maths, but I like to introduce in a way so that all of you could find something of their interest in this particular topic. And I hope for some students who are in universities and who are preparing for IIT JEE exams, this could be a very helpful video. We'll basically introduce you to hyperbolic functions. These are the three: sine hyperbolic x, cos hyperbolic x, and tan hyperbolic x. We'll sketch graph of these functions, write their domain range, and take up hyperbolic identities and also see what is the link between circular, means trigonometric functions, and the hyperbolic functions, correct? Now, to begin with, we have already given the definition, which is sine hyperbolic x is equal to e to the power of x minus e to the power of minus x divided by 2. So you can see these are basically exponential functions combination, correct? So let me just review e to the power of x graph with you first, and then we'll move on and talk about these hyperbolic functions, right? I hope that makes sense, right? Now, e to the power of x and e to the power of minus x. Now, if a graph is dropping down, we know the exponent is negative, correct? So this is the graph of e to the power of minus x, correct? On the other hand, if I have a graph which is rising, always increasing, exponential graph, it could be the graph of e to the power of x. So these are the two graphs we are working with when we talk about cos hyperbolic x, correct? And when we introduce you to sine hyperbolic x, we have here minus e to the power of minus x. That means this particular graph will be reflected on the x-axis, correct? So this is your x-axis, this is y-axis. So reflecting it, we get something like this. So this graph is minus of e to the power of minus x. Perfect. So that is how we'll be in a position to define these hyperbolic functions. We'll begin with cos hyperbolic x since it is addition of these two. What I will also do is actually write this as half of e to the power of x minus half of e to the power of minus x, and this as combination of half of e to the power of x plus half of e to the power of x, correct? And as far as tan hyperbolic x is concerned, we'll treat this as sine hyperbolic x over cos hyperbolic x. So that way, they are very similar to trigonometric functions as far as operations are concerned, correct? So let's begin with the cos hyperbolic x. So we'll take these two functions, right? We'll just add them up to get cos hyperbolic x. For sine, we'll take half of these, correct? These two, add them up, and then get the graph, and from there we'll talk about domain range. So I hope that is simple enough to understand, right? So let's take up cos hyperbolic x now. Now let us write down cos hyperbolic x as combination of exponential functions e to the power of x over 2 plus e to the power of minus x over 2, right? So half of these. Let me first sketch the graph, and then we are going to write domain and range after sketching the graph of cos hyperbolic x. So e to the power of minus x, I'll draw first like this. Now this one is, I've sketched here, this position is half. That means this function which I've sketched is basically e to the power of minus x divided by 2, correct? Now for the positive part, e to the power of x divided by 2, it is going to go through half, right? That is your y-intercept, and that is going to be your function. Now clearly, growing function e to the power of x over 2, right? So these are the two parts. And when you add them up, what you get? You get cos hyperbolic x. Perfect. So these values combine, half plus half, you get 1, and you'll see. So it is always greater than 1, correct? Now if this is very high, that is low. So it is approaching this side. So 1 is important point, correct? Twice this. And to this side, it approaches this function, kind of. Do you see that? As we go, since that green line is much lower, and if you move on this side, it approaches the green portion because the value of that is higher. It's just a smooth curve approaching this, right? So I haven't drawn it so well, but it's like perfectly symmetrical, right? So let me show it by saying that it is perfectly symmetrical. Okay, so what I will do here is kind of sketch. It's an even function, just as cos is even function, so it doesn't look like, but say this is equal, right? Okay, so it makes sense. If I do minus x, we get the same expression. Okay, so that's what it is. So what you learned here is that this particular function, cos hyperbolic x, is even, right? So we can say, first property, that cos hyperbolic x is an even function. It is symmetric about y-axis, right? This is very important property. So that gives you an idea that cos hyperbolic of minus x will be equal to cos hyperbolic x, correct? So this property is very similar to what you found for cosine x, correct? So similarly, as we move along, we'll find a lot of similarities between trigonometric functions and the hyperbolic functions. However, remember always that hyperbolic functions are basically exponential functions, correct? Now let's talk about its domain and range. Now domain, clearly you can see there is no restriction, correct? So x belongs to real numbers. As far as the range is concerned, what is the range for this function? The y value, which you see is always greater than 1, right? When you combine half and half, you get 1. So y belongs to real numbers where y is greater than equal to 1. Simple as that. So I hope up to here there is no problem, correct? You can also see that when x approaches negative infinity, in that case cos of hyperbolic x approaches what? It approaches e to the power of minus x. It approaches infinity, which is positive. So it's like but it approaches the value of e to the power of x, correct? And when x approaches positive infinity, in that case also cos hyperbolic x approaches positive infinity, right? That you could treat this as your end behavior, correct? So the value is always greater than equal to 1 and could be infinitely large. However, you could also see that the function approaches e to the power of x for a higher value. When x is higher positive, e to the power minus x for a negative value. Perfect. So I hope till here there's no question. Let's move on and look into sine hyperbolic function and its graph. So sine hyperbolic x can also be written as half of e to the power of x minus half of e to the power of minus x, correct? So we can take the graph of exponential functions and then add them up. So in this case, the two graphs of our interest will be one, half of e to the power of x, which is kind of growing, right? Kind of like this, where this point is half and this is e to the power of x. Perfect. The other part is reflection of e to the power of minus x. So e to the power of minus x was kind of like this. So when you reflect it, it will look like what, right? So at that time, when you reflect it, it is going to be kind of like this. So this is e to the power of minus x by 2. Let me write half. I didn't write half there. Okay. E to the power of half of e to the power of x. Does make sense? Since this point is half, this point will be minus half. Okay. Now that is how it is. So we have to combine these two graphs. Is it okay? So if you combine these two graphs, you get the graph for sine hyperbolic x. Correct? So it is kind of like this. It approaches this part when e is, because this is very small, 0, right? It will be almost same as this, correct? On this end, it has to go through 0, so it will be kind of like this, and then it turns towards this side. Is it okay? Closer to, as we go infinitely large value, it goes closer to e to the power of half of e to the power of x. It does make sense to you, right? So that is how the graph of sine hyperbolic x is going to look like. Now from here, you can easily write down the characteristics, correct? Now one of the most important characteristics which you see here is that it is an odd function. So we can see that sine hyperbolic of minus x is minus sine hyperbolic x, correct? It's an odd function. And now let's look into domain and range of sine hyperbolic x. So as far as domain is concerned, there are no restrictions, correct? Domain is x belongs to real numbers, as we saw for cos hyperbolic x. Range, is there any restriction on range? Not at all, right? So range is also all real numbers. How about end behavior? As far as end behavior is concerned, we say that if x approaches negative infinity, y approaches negative infinity. And if x approaches positive infinity, then y approaches positive infinity, right? So this is x. So that is the behavior of this function. So I hope that is absolutely clear. Now let's continue with tan hyperbolic x. Now let's look into graph and domain range of tan hyperbolic x. It is given as e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. We can always write tan hyperbolic x as equal to the ratio of sine hyperbolic x over cosine hyperbolic x, correct? Now, the graph of this function will look like something like this. There are no restrictions to this function, since sine hyperbolic x is always greater than 1. So if you sketch this graph, what we see is that it has two horizontal asymptotes, one for plus 1 and one for y equals to minus 1. Sine function, as you know, is sine hyperbolic x is kind of like this, right? Now, divided by the cos, you get a function which is like this. Where y equals to 1 is one of the horizontal asymptote and y equals to minus 1 is the other horizontal asymptote. Now this graph, as you can see, is symmetric about origin, right? And therefore, we can say this is an odd function, just as sine hyperbolic x. Now you can always write its domain and range from the graph. Domain is all real numbers, And what is range? Is all the numbers between plus and minus 1, right? So it is never equal to, but it's always greater than minus 1 and less than plus 1. So that becomes the range for the function tan hyperbolic x. So I hope that part is clear. So we have seen all the three functions, sine, cosine, and tan hyperbolic x. Now as an exercise, what you can always do is make graph for cosecant hyperbolic x, which is same as 1 over sine hyperbolic x. You can do secant hyperbolic x, which is same as 1 over cosine hyperbolic x, and cotangent hyperbolic x, which is same as 1 over tan hyperbolic x. So let this be your exercise. Now let's move on and look into some identities related with hyperbolic functions. Now we have very similar identities for hyperbolic functions as we have seen in trigonometric functions. We have already seen a couple of them. One is sine hyperbolic minus x is equal to minus sine hyperbolic x. Now this is an odd function, and therefore, as we saw, it is always true. Similarly, cos hyperbolic minus x is equal to cosine hyperbolic x, and tan hyperbolic minus x is minus of tan hyperbolic x. Now you saw that this is because these functions are, this is an odd function, right? This is an even function, and tan is again an odd function. Now apart from this, we have similar to trigonometric identities, Pythagorean trigonometric identities, which are 1 minus tan hyperbolic square x is secant hyperbolic square x, right? Well, I should first write cos hyperbolic square x minus sine hyperbolic square x is always equal to 1. So these are trigonometric type of identities which we have for hyperbolic functions. Now we'll try to see, rather prove them also in this video. Now we also have those sum of angle types. Sine hyperbolic x plus y could be written as sine hyperbolic x cos hyperbolic y plus cos hyperbolic x times sine hyperbolic y. For cosine hyperbolic x plus y, it is cos hyperbolic x times cos hyperbolic y plus sine hyperbolic x sine hyperbolic y. Now these are the identities which are true for all the hyperbolic functions, and we can always prove them by knowing that well, we know what sine hyperbolic x is, right? We know sine hyperbolic x is equals to e to the power of x minus e to the power of minus x over 2. Cos hyperbolic x is equals to e to the power of x plus e to the power of minus x over 2. And tan hyperbolic x is equal to ratio of these two, right? E to the power of x minus e to the power of minus x by their sum. Right. So to prove these identities, we can actually substitute the exponential form, right? And then we can show that left side is equal to right side. So let me do it for one of our functions. We'll take up cosine hyperbolic square x minus sine hyperbolic square x equals to 1 and prove it. So let us try to prove one of these identities. We'll take up cos hyperbolic square x minus sine hyperbolic square x equal to 1. Now cos hyperbolic x, is e to the power of x minus e to the power of minus x over 2. So we'll square this, right? This is positive, sorry. And this is e to the power of x minus e to the power of minus x over 2. We'll square this also. So that is our left hand side. So let's begin with the left hand side. So when you square, what do you get? You get 4 in the denominator, and here you get e to the power of square of this, which is 2x, plus 2 times e to the power of x times e to the power of minus x, plus e to the power of minus 2x, correct? That's what you get. And on this side, you get, again 4 in the denominator, you get e to the power of 2x minus 2 times e to the power of x times e to the power of minus x plus e to the power of minus 2x, right? Now, the center term is just 2, correct? So, taking common denominator as 4, we get 1/4 of what? So, we can write this as e to the power of 2x plus 2 plus e to the power of minus 2x. And on this side, we have negative e to the power of 2x. That negative makes it positive 2. And here we get negative e to the power of minus 2x. So clearly, e to the power of 2x cancels with this term, and the other term also cancels, right? So we are left with just 4 inside the bracket. 2 plus 2 is 4. So we're left with 1 over 4 times 4, which is indeed equals to 1, and that is right hand side. Correct? So using these basic exponential equivalent of hyperbolic functions, you can prove all the identities. So as an exercise, you can try the others. I hope that makes sense. Now let's move on and try to understand how these hyperbolic functions get their name and some of their links with our trigonometrics, which we also call as circular functions. Now let's also take up the other identity, beginning from cos hyperbolic square x minus sine hyperbolic square x equals to 1. We just proved it. Now if I divide by cos hyperbolic square x for each term, what happens? Let's divide by and then see what happens, right? So if you do that, you get cos hyperbolic square x divided by cos hyperbolic square x minus sine hyperbolic square x over cos hyperbolic square x equals to 1 over cos hyperbolic square x. Now this term is 1, and here we get tan hyperbolic square x, and this is secant hyperbolic square x, right? So that's the next identity, correct? So that is how you could actually easily prove these identities. Their proof is very similar to what we did for trigonometric functions. Perfect. So there we are. We'll take some examples and prove some more identities using these hyperbolic functions. And now let's try to understand similarities between these hyperbolic functions and trigonometric functions, which are also known circular functions. Now we will see some more links between circular functions, which are trigonometric functions, and hyperbolic functions. So let's get back to our unit circle. So let us say if this is the unit circle, in that case, any point on this unit circle can be represented by what? The cos value is the x, right? So we can say cos t sine t for a unit circle. Perfect. Now for a unit circle, you know that the radius is going to be 1. Let's say this angle here is t. Now we know this identity, cos square t plus sine square t equals to 1, right? So that is why these are also called circular functions. And what we just proved was cos square, I should say hyperbolic square x, we could use t for any real number, minus sine hyperbolic square x is equal to 1. Now if you correlate, what is the equation of a circle? Equation of circle is x square plus y square equals to 1, right? And what is the equation for hyperbolic function? It is x square minus y square equals to 1. So that relates. Do you see that? So that gives the name hyperbolic function. Now if I sketch a hyperbola, it will look something like this. Let's say we have a hyperbola like this, right? And here like this. In that case, any point on this hyperbola, let's say this particular point, can be written as cos hyperbolic t sine hyperbolic t. This x square minus y square equals to 1, cos hyperbolic square minus sine hyperbolic square equals to 1. Perfect. And the relation between the trigonometric functions and hyperbolic function, one more relation is kind of this. If you see the area of the sector, now, so we'll talk about now area of sector. So let me say area of circular sector first, which is this particular portion here. Now if the angle is t in radians, any real number, in that case what is the area of this shaded portion? Well, you know pi r square area of sector is what? Pi r square is the total area, right? Area of the sector will be ratio of the angle, which is t over 2 pi. 2 pi being full angle, correct? Now since r equals to 1, right? So r is 1, pi and pi cancel. So we get area of sector equals to, so let me show you here. This pi and pi cancels, r is 1 equals to t over 2, or that gives us t as twice the area of sector. Does make sense? So for circular functions, what you see is that t is twice the area of the sector. Here also, if this is t, in that case, I mean, it's not really the angle, but the position cos hyperbolic t sine hyperbolic t for any coordinate point here, in that case, area of this sector, so in this case, this t is also equal to area of, we can call it hyperbolic sector. In quadrant 1 times 2. So we should say times 2. So twice the area, just as this formula, correct? So that is another relation which is kind of similar to hyperbolic functions and trigonometric or circular functions. So in this video, we learned so many similarities between these two functions, and also we kind of understand now how the name has been put as hyperbolic function, mainly because cos hyperbolic x square of cos hyperbolic x minus sine hyperbolic x equals to 1. So any point here could be represented by this particular function, just as we are doing for trigonometric functions, right? So circle x square plus y square equals to 1, hyperbola x square minus y square equals to 1 gives that kind of correlation. And also when we are working with identities, we saw so many similarities. So working with hyperbolic functions is quite similar to what we did with trigonometric functions. However, you should understand these are not trigonometric functions. They are representing exponential functions, right? So I hope that point is absolutely clear. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'll be great. Thanks for watching and all the best.